Welcome back to Module 6, Bias and Fairness. In this lecture, we will talk about fairness. We will have an introduction to the topic, we will see the 4 types of fairness, and we will check a practical example. When we evaluate the fairness of a machine learning model, defining what constitutes fairness can vary significantly. Let's consider a scenario involving a credit card application approval model. Would it be fair if the approval rate were equal across genders, or would it be preferable to remove gender information from the dataset and shield it from the model? We will explore different criteria for fairness, gaining insight into different dimensions. We consider a scenario where we are dealing with a model responsible for choosing individuals to receive a particular outcome. This outcome could involve approving individuals for a loan, admitting them to a university, or offering a job opportunity. It's important to note that we are not considering models performing tasks such as facial recognition or text generations, focusing specifically on models that make decisions about application of opportunities or resources to individuals. Note, it is crucial to recognize that there are additional methods for formalizing fairness, and I encourage you to delve into them. Demographic parity. Demographic parity suggests that the model is fair when the selection made by the model mirrors the demographic distribution of the applicants. For instance, imagine an university admission process where an admissions model is used to select candidates for a highly privileged program. If 40% of the total applicants are from rural areas, the model, in adherence to demographic parity, would aim to ensure that 40% of the selected candidates also hail from rural backgrounds. This approach strives to maintain consistency between the demographic composition of the selected group and the overall distribution among the applicants, fostering a sense of fairness in the selection process. Equal opportunity. Equal opportunity fairness ensures that the model selection of individuals who should be identified, it's the positive for example, is done in the same accuracy across all demographic groups. This accuracy is quantified by the true positive rate, also known as the sensitivity of the model. For example, consider a scenario where a doctor employs a tool to identify patients requiring additional care, potentially at risk of developing serious medical conditions. This tool, acting as a supplementary second opinion to the doctor practice, is specifically designed to have an high true positive rate that remains equal for each demographic group. In other words, the tool aims to accurately identify patients in need of extra care with consistent effectiveness regardless of the individual's demographic characteristics. This approach seeks to ensure fairness in the identification of individuals who may require additional medical attention. Equal accuracy. Equal accuracy is a fairness criterion that ensures the model achieves the same level of accuracy for each demographic group. The percentage of correct classification, whether it is approving individuals who should be approved or denied those who should be denied, should be consistent across all groups. Equal accuracy is a fairness criterion that ensures the model achieves the same level of accuracy for each demographic group. The percentage of correct classifications, whether it is approving individuals who should be approved or denying those who should be denied, should be consistent across all groups. Let's imagine an online platform using a content recommendation system to suggest articles to its users. The platform aims to ensure that the system exhibits equal accuracy for users from different regions. In this context, if the recommendation system achieves 90% accuracy for users in one geographical region, it should strive to achieve the same 90% accuracy for users in other regions. This way, the platform aims to provide equal, accurate, and relevant content recommendations, regardless of the user geographic location. This approach helps prevent biases in content suggestion and ensure that users from diverse regions receive recommendations with fairness and consistent accuracy. Fairness through awareness involves the removal of all information related to group membership from the dataset. This process aims to eliminate potential biases associated with specific demographic attributes. For example, gender data may be removed to promote fairness across different gender groups, and a similar process can be applied to race or age information. Let's suppose a company is using a machine learning model for employees' performance evaluation. To ensure fairness and eliminate potential biases related to ages, the company decides to adopt a group-unaware approach. In doing so, they remove all age-related information from the dataset used to train the model. However, challenges arise in practice. If the dataset contains information such as year of experience or educational level, these variables may serve as proxies for age. Therefore, to truly achieve group awareness fairness, the company must carefully identify and eliminate any indirect indicators of age to prevent the model from making inferences about an employee's age based on the remaining data. While group-unaware fairness is a step toward mitigating biases related to the age, the company needs to exercise caution to ensure that no unintended proxies for ages or other group-related attributes remain in the dataset, thus promoting a more equitable and fair employee evaluation process. Let's check a practical example. We will use a concise example now to highlight the distinctions among the four types of fairness. We use the confusion matrix, a widely used tool for assessing the performance of a machine learning model, to illustrate the concepts. The example below showcases a model with 80% accuracy, correctly classifying 8 out of 10 instances and an 83 true positive rate, accurately predicting 5 out of 6 positive. To understand the variations in a model performance across distinct groups, it is beneficial to create separate confusion matrices for each group. In our example, we assume we have data from a relatively small sample of 20 individuals evenly divided between two groups, 10 individuals from group A and 10 individuals from group B. The following illustration shows the potential structure of confusion matrices under the assumption that the model adheres to the principle of demographic parity fairness. Specifically, the model evaluates 10 individuals from each group, ensuring an equal representation of 50% from both Group A and Group B. Subsequently, the model approves 4 individuals, maintain an equitable distribution of approvals with 50% from each group, a manifestation of the demographic parity fairness principle. In equal opportunity fairness, maintaining uniformity in true positive rate across different groups is crucial. In the provided example, this uniformity is evident with a consistent true positive rate of 66% observed from each group. This parity underscores the commitment to equal opportunity fairness within the model performance evaluation across various demographic groups. The confusion matrices for equal accuracy fairness are shown below. Fairness through unawareness is not discernible from the confusion matrix. Its focus is on removing group information from the dataset. Let's reflect on the toy example to grasp the nuances between fairness types. Consider how the scenario changes if Group A has double the applicant of Group B. None of the examples simultaneously satisfy multiple fairness criteria. For instance, the demographic parity example does not align with equal accuracy or equal opportunity. You can verify this. In practice, optimizing a model for more than one fairness criteria is usually impossible, as explained in the impossibility theorem of machine fairness. Choosing a fairness criteria involves nuanced team discussions. In real projects with larger datasets, confusion matrices aid in analyzing model performance. Real-world models rarely achieve perfect fairness. For instance, even if aiming for demographic parity, the model may select around, but not exactly, the percentage requested. What we have learned in this lesson. When we evaluate the fairness of a machine learning model, define what constitutes fairness can vary significantly. We will explore direct criteria of fairness, gaining insight into different dimensions. Demographic parity suggests that the model is fair when the selection made by the model mirrors the demographic distribution of the applicants. Equal opportunity fairness ensures that the model selection of individuals who should be identified like positive is done in the same accuracy across all demographic groups. This accuracy is quantified by the true positive rate, also known as the sensitivity of the model. Equal accuracy is a fairness criterion that ensures the model achieves the same level of accuracy for each demographic group. Fairness through unawareness involves the removal of all information related to group's membership from the dataset.